Hello, so in today's video, we're going to differentiate the function ln of sec of x, so the natural logarithm of the secant function. And to do this, we're just going to use a result from a previous video. So we know that when we differentiate the natural log of cosec of x, we got negative tan of x. So this is a result from a previous video. So previous video, so you can just check that out using by watching one of my previous videos where we differentiated this function already. So we're going to use this result here. So we know that sec is just the same as 1 over cos. So this is literally just the same as differentiating the natural logarithm of cos of x to the power of -1, like that. And then using our laws of logarithms, we can bring this power to the front of the logarithm. And if we do that, we get the derivative with respect to x of negative ln of cosine of x. And then again, we've got this -1 here. We can just bring that outside the differential operator. So negative d by dx of ln cos of x. And we know that this result over here, because, well, we know that the derivative of ln of cos of x is going to be negative tan of x, because we did this in a previous video. So this is going to be the negative of the negative of tan of x, this final result down here. So negative tan of x. So that's just positive tan of x. So when you differentiate the natural log of sec, you get tan of x. So that's our conclusion there. Let's just consider, to finish off with, the domain of x values in which this result holds true. Well, in order for ln of sec of x to be defined, so ln of sec of x is defined when, so we need two things to happen. We need sec of x to be greater than 0, because otherwise the natural log function isn't defined. So we need sec of x to be greater than 0. We also need sec of x to be defined itself. So sec of x must be defined. And when is sec of x defined? Well, this is defined when cos of x does not equal 0. Because if cos of x equals 0, then sec of x is 1 divided by 0, which is undefined. So if we just consider this first point here, so when is sec of x greater than 0? Well, we know that a secant graph kind of looks something like this. So you've got your asymptotes at pi over 2 there. You've got another one here at 3 pi over 2. You've got one here, negative pi over 2, and so on and so on. And the graph kind of goes like this. So where is sec of x greater than 0? Well, it's greater than 0 when x is in this set here. So the set between minus pi over 2 and pi over 2. And also, if we continue in the positive direction from 3 pi over 2 to 5 pi over 2, and so on and so on. And also in the negative direction too. So negative 5 pi over 2 up to negative 3 pi over 2, and so on and so on. So how can we write this set in a more efficient way? Well, we can just say that this is the set of x values for which x is between, so 4k minus 1 times by pi over 2 up to 4k plus 1 times pi over 2. So why does that work? Well, I mean, if we look at this sequence of numbers here, so that number to that number, we're jumping up in multiples of 4 lots of pi over 2, and the sequence -1, 3, 7, and so on and so on. That nth term is just a 4k minus, well, that kth term is a 4k minus 1 kth term. So if we multiply that by pi over 2, we get these first terms, and then these second terms, they're just going to be, so again, we're jumping up in multiples of 4 of these pi over 2 values. So 1 to 5 to 9, that's got a kth term of 4k plus 1. So 4k plus 1 multiplied by pi over 2, that's how we get these kth term values here. So therefore, this derivative is defined for x values in this domain here. So yeah, so just to conclude the result, so when we differentiate the natural logarithm of sec of x, we just get tan of x, and this is valid. So valid when x is between 4k minus 1 times pi over 2 up to 4k plus 1 times pi over 2, where k is just an integer, where k is an integer value. And yeah, that's what we showed back here. So yeah, that concludes the result for this video here.